Lots of applications of these types of things. Section 15.6, Geometric Series. So, if you recall it from the last section, an arithmetic series was a series where the individual terms that you're adding were from an arithmetic sequence. In a geometric series, each of the terms in your geometric series is just a term in a geometric sequence. So notice 3 multiplied by 2, 6 multiplied by 2, 12 multiplied by 2, 24. So I'm just adding up a whole bunch of terms in a geometric series. And so let me find the sum of a geometric series. So let's do the following trick. Let's call S of n the, well, I guess we should note. So for general term of a geometric series, it's just R, just A sub 1, R to the n minus 1. And maybe I'll write it as a K, just so that it looks a little nicer. So then, the sum of the first n terms of a geometric series well, is just, let me again, this will be the sum k equaling 1 to n of a1 r to the k minus 1. So if I just look at the sum of the first n terms of this geometric series, I get that it's equal to a1 r the n minus 1 over r minus, let's do it as 1, actually let's write it the other way. 1 minus r to the n over 1 minus r. Of course, in this case, I'm assuming that r is not equal to 1, so I'm not dividing by 0. Of course, in my geometric series, I made the blanket statement that I assumed that r was not equal to 1 because it wouldn't be a very interesting geometric series. Um, and so, um, let me derive this. And so let me let S of n just denote the sum of the first n terms. In this case, it's for geometric, but in the previous section, I let it be the notation for arithmetic, but I'll just let it be the same thing for geometric. So if I look here, the first term is a1, the next found by multiplying by r, like we did here up here where we multiplied by 2, then keep multiplying by the same thing up until you get to the last term. Now, let me multiply by, well, let's say negative r. This will equal, well, negative a1r minus a1r squared and minus a1 r to the n minus 1 minus a1 r to the n. And let's add these up. So if I do that, I'll get s sub n minus r s sub n. The a1 r1, a1 r's cancel, a1 r squares, dot dot dot, all the way up to a1 r to the n minus 1's cancel. So all I get is a1 and the first term a1 and the last term a1 r to the n. Let me factor out s to the n, s sub n. So you get 1 minus r s sub n. Factor out a1, you get 1 minus r to the n. Divide by 1 minus r. Of course, I'm assuming that in this case r is not equal to 1, so I'm not dividing by 0. And so this is equal to my formula, a1, 1 minus r to the n over 1 minus r. And that's what I wanted to derive. Let's do some examples. Let's say on page 674, oops, sorry. So page 674. Let's say problem number, how about 1? Yeah, let's do problem number 1. 1, 3, 5, 7, 9, etc. In exercises 1 through 6, determine whether the series is geometric or not. So I want to determine if this series is geometric. So let me do that. And so if I look here, well, I keep adding 2. And so no, it's not geometric. I don't multiply by a constant. I'm adding the same constant. So this is not geometric. It is an arithmetic series. Okay. So no, that's not good. How about problem number 6? No, how about problem number 5? 1/5, negative 1/5, 1/5, negative 1/5. So I'm adding 1/5 plus negative 1/5 plus 1/5 plus negative 1/5. This is geometric. Because I'm always multiplying by negative 1 to get to my next term in the sequence. And so I'm adding up a geometric sequence. Therefore, this is a geometric series. Let me do problem number 7. 1 plus 1/3 plus 1/9 plus 1 over 27, etc. Determine whether in exercises 7 through 9, determine the sum of the first 15 terms of the geometric series. So I want to figure out the sum of the first 15 terms. Well, I know that the sum of the first n terms of a geometric series, I called it S, is A1, 1 minus r to the n, 1 minus r. So let's find the sum of the first 15 terms. And so if I find the sum of the first 15 terms, then the first term is 1. The common ratio, well, this is going to be much, is 1/3. And I want to add up the first 15 terms. Okay. And so let me do that. So this is equal to 1 minus 1 over 3 to the 15 over 1 minus 1/3. Let's multiply by 3 to the 15 and divide by 3 to the 15. And so this is just equal to, well, 1 times 3 to the 15 is just 3 to the 15. 3 to the 15 divided by 3 to the 15 is 1. 1 times 3 to the 15 is 3 to the 15. 3 to the 15 divided by 3 is 3 to the 14. So I get, well, 3 to the power 15 is a rather large number. And so it is 143, 489, 907, and subtract 1, you get 906. Okay, so 14,348,907 minus 1 is 906. Then take 3 to the 14, 3 to the 15, subtract from it 3 to the 14, and so you get 95, 6, 5, 9, 3, 8. Okay. And so you get somewhere around 1.5. Okay. Let's see. Let's divide each of these by 2 at least. Seven, 1, 7, 4, 4, 5, 3 over 48, 47, 8, 2, 9, 6, 9. Okay. Okay, so that's the sum. I don't think you can divide by 3. That's 8, 16, 24, 31. Good. Okay, so not divisible by, I think it's divisible. I don't think those are divisible by anything. So the sum of the first 15 terms is 71. 7,174,453 over 4,782,969, which is approximately 1.5, 1.4245. 1, 2, 3, 4, 5, 8, 9, 5, approximately. So it's somewhere in that order. It's around 1.5. Okay. Let me do problem number 10. One, 2, 4, 8, etc. In exercises 10 through 15, find the expression for the sum of the first n terms of the geometric series. Okay, so let's do that. And so the sum of the first n terms is just a1. Since r here is greater than 1, let me write it as r to the n minus 1 over r minus 1. I just flipped it around, both the numerator and denominator, since in this case r is greater than 1. And so this is equal to a1, which is 1. R in this case is 2. I keep multiplying each term by 2 to get to the next term. 2 minus 1. Well, 2 minus 1 is just 1. And so the sum of the first n terms is just 2 to the n minus 1. And that is your answer. So if you just add 1 plus 2 plus 4 plus 8, add up n of those, you get 2 to the n minus 1. Okay. Let me do let's do the first. So that was 10. How about problem number 12? Three minus 6 plus 12 minus 24, etc. And so let's try to find the general term for that. And so, again, S sub n is equal to a1. Again, since r is greater than 1, I'll write it as r to the n minus 1 over r minus 1. And so, in this case, the first term is 3. I'm always multiplying by negative 2 to go from 3 to negative 6 to positive 12 to negative 24. So r is negative 2. And I have a negative 2 minus 1. And so this is equal to 3 times a negative 2 to the n minus 1 over negative 3. Well, I can cancel the 3's, and I just get a negative 1. And so that says change all these signs. So I'll just reverse the order. I'll make it as a 1 minus negative 2 to the n. And so if I add up the first n terms, I can just use this formula to calculate its sum. 14. I like 14. Let me do problem number 14. 4 plus negative 4 plus 4 plus negative 4, etc. Okay, so let's find the sum of the first n terms of this. Again, since r is greater than 1 in absolute value, I'll write the formula this fashion. Well, in this case, the very first term is 4. The common ratio. Notice that to go from 4 to negative 4 to positive 4 to negative 4, I keep multiplying by negative 1. And so the common ratio, r, is just negative 1. And so negative 1, I'm sorry. And so negative 1 minus 1 is a negative 2. 4 divided by negative 2 is a negative 2. And maybe I will change the sign because it'll look a little nicer. And so let me multiply just the negative, just this negative inside. Oops. So I'll only multiply this negative. And so this becomes 2. Then minus 1 becomes a plus 1. And the plus in front of the negative 1 then becomes a minus. And so if I add up the first n terms of this series, I just get 2 times the quantity 1 minus a negative 1 to the n. It basically keeps alternating between 0 and 4. And so it's either going to be 4 or 0, the sum of these. Okay. Now note that if, in this case, r, let me look up in this form, if in this case r was small, then this term, for n being large, this term is going to be exceedingly small. And so as n goes to infinity, as long as r is small, this term will be insignificant. And so for we have a value for an infinite geometric series. So an infinite geometric series. Let's find the formula for that. And so if I just add up all of these, and maybe I'll use n in this case. Then either the sum will be, well, a1 over 1 minus r. This is if r is small. Otherwise, if r is bigger than 1, we say that it diverges, that it gives us a strange answer. Okay, so either you're going to be adding up a whole bunch of terms that are bigger than 1, and you're going to add a whole bunch of terms that are aren't going off to 0, or or adding, subtracting things. So basically you're adding or subtracting things and they don't necessarily become smaller and smaller. So your answer becomes difficult to answer. So we say that it diverges, gives us a divergent answer. Okay. So Let's do this. Let's do problem number, I don't know, that's 16. So 16. Let's do problem number 16. Which is to find there. The following sum: 1 plus 1/3 plus 1/9, 1 over 27, 1 over 81, etc. So I want to find the sum of all those. And so this is equal to, well, let's see. If r is less than 1, then I know what's happening. If not, I don't know what's happening. So let's see. Well, what's r? Notice that to go from 1 to 1/3, I multiply by a third, multiply by a third to get 1/9, multiply by 1/3 to get 1 over 27. So r is, oops, 1/3, which implies that the absolute value of r is 1/3, which is less than 1. Good. So that means that I have the following formula, that the sum of all the infinite number of terms, starting from 1 going all the way out to infinity, is just going to be a1 over 1 minus r. And so let's figure out that sum. It's equal to a1. a1 in this case is 1. r in this case is 1/3. So let's multiply and divide by 3. So 3 times 1 is 3. 3 times 1 is 3. 3 divided by 3 is 1. And 3 minus 1 is 2. So if I add up 1 plus 1/3 plus 1/9 plus 1 over 27 plus 1 over 81 and keep doing that forever, then I'll come out with 1 1/2. Okay, so the 1/3 plus 1/9 plus 1/27 dot dot dot, that gives me 1/2 more. Let me do problem number 19. One plus 2 plus 4 plus 8 plus 16. And so let's find the sum of those. Well, notice that in this case, the common ratio r is 2, which says that the absolute value of r is greater than 1. Therefore, this infinite geometric series gives us a very strange answer. It is said to diverge. So it gives us this divergent answer. So notice that, you keep adding up all these bigger and bigger and bigger numbers. Okay. Let me do problem number 22. And so, a king so this is actually a old Persian story about the invention of chess, and it's sort of retold here in a little different light, but the original story was about the person who invented chess, and so the king was very grateful for it and asked for a certain, if they could, if he could give him a certain sort of compensation for it, and this was the compensation that the person theoretically, or was so told in the tale, asked for. So a king. When I originally heard it, I guess it was that a person saved someone and then they asked for, I guess, wheat. But we're going to say rice. The original story, the original Persian story, was actually they asked for dates. Actually, for just date flour. Um, but we're going to do it with rice, just because rice is easier to calculate. So, a king who was said, who was very fond of chess, was saved by a person in a forest. The king was very happy and grateful and asked the person for a wish. So since the person saved the king's life, well, I guess I'll grant you a wish. Tell me what you want. This person said, very humbly, "Oh, my master, if you want to grant me a wish, then please give me 1 grain of rice for the first square of a chessboard, 2 for the second, 4 for the third, 8 for the fourth, and so on. So this doesn't sound like a lot. So it's like, just want a few grains of rice. So that doesn't sound too bad. The king said, sure, why not? That sounds reasonable. The king was amazed at this wish. And promptly granted it. Okay. It is said that the king ran out of rice and could not fulfill the wish. And so our question is explain why this is so. Okay, so let's do this. And so, well, what was he asking? And so he was asking for 1 grain on the first, 2 on the second, 4 on the third. So every time, and 8 on the next. So every time he was just doubling the previous amount on the square. And so this is just going to be some geometric sequence. And then he asked for all of them, so he wanted to add them all up. And so it was just, well, let's see, 1 grain, 2 grains, 4 grains, 8 grains, etc. Okay, so that's not too bad. And, well, on a chessboard is an 8 by 8 chessboard. And so, there it is. So chessboards are 8 by 8. So they have 64 squares. So therefore, we're going to be adding up 64 terms. Okay. And so, I know the formula for the term, for the sum of the first n terms is just a1 r to the n. Let's bring it down a little bit more. The sum of the first n terms is a1 r to the n minus 1 over r minus 1. Okay, so let's do that. And so we want to find the sum of the first 64 of these terms. The first term is 1. And notice I'm doubling each time. And so the common ratio is 2. 2 minus 1 is just 1. So this is 2 to the 64 minus 1. And so, let's figure out how much that is. Well, it becomes then I sort of ran out of calculator. Grains. So 1,000, million, billion, trillion, quadrillion, quintillion. 18 quintillion. So let's do this in kilograms. So notice that 1 grain of rice is 1 gram of rice. And so this is also grams. So 1 grain of rice is approximately 1 gram. And so this is actually it's wait 1 second. So 100, I'm sorry. So if I look at 100 grains, that's 1 gram. Yeah, 100 grains is 1 gram. So 100 grains of rice is 1 gram of rice. So I guess let me divide this by 100. So if I do that, I get 184. 446. Oops. 184. 467. 440. 700. Grams of rice. So 1,000, million, billion, trillion, quadrillion. Okay. And let's do kilograms. These are kilograms of rice. So that's 1,000, million, billion, trillion. 184 trillion, which is 184, 467, 440, 700. Okay, good. I only have the last 2 zeros I'm not sure about. Metric tons of rice. And so, 1,000, million, billion. 184 billion, 467,440,700 metric tons of rice. So that's a lot of rice. Okay. And so, that's more rice than is produced currently in the world. So that's just a lot of rice. Um, so let me give you some practical applications of this. Applications involving money. Annuities. Well, let's first recall simple interest. So, the amount of money you make over one period would be um, P times 1 plus R. Okay, so let's do an annuity, a simple annuity. So annuities are financial instruments where you either put money in to an account at a steady rate. You always put in $1,000 every month, or it could be where you always take out the same amount, or like in mortgages, where you always pay back the same amount. And so let R, and let me just figure out the formula for some sort of period, the period at which we have the interest. So the interest rate per period. Let N be the number of periods. And let P be the principal. And so this is the amount input into the annuity. Per period. Okay. So this will make some of our calculations easier. And so let's figure out how much you have. Well, you initially put in P dollars. Then for the next month, um, you put in P dollars again. But that previous month earned interest at a rate of R for that period. So the amount that you have for the current period is, well, you put in P, but then you also had P times 1 plus R from the previous amount. Next, you put in another P. Well, for the one that you only had for one period, it's P times 1 plus R to the first. For the one that you had in for two periods, it's P times 1 plus R to the 2. And you keep doing that up until the last one, which you have put in P for the very last time that you put in your amount. And for the very first time, well, you've had it since the very beginning, since your last N periods. And so you have interest for it for N minus one of those periods. So, well, this is just a geometric series. And so the formula for your geometric series was Sn is equal to A1. Oh, I see. R to the n minus 1 over R minus 1. Okay, so let's do that for this. In this case, the very first amount, A sub 1, was P. R in this case is actually 1 plus R. and you do it for n, so that's good. 1 plus r minus 1. Now the 1's cancel, and so I get the formula. A equals P, 1 plus r to the n minus 1 all over r. And so that is the formula for a simple annuity. Okay, so let's do some examples. Let's say the following. Mr. Good Father invest, let's say $50. Well, let's do $100 per month. Into for 20 years. For 20 years into an IRA. Let's say Roth IRA. So you don't need to pay any taxes into a Roth IRA for his newborn, for his son, his newborn infant son. For his infant son. At 12% interest compounded per month. Okay. Well, when the son grows up, you know, the son does not put any additional money into the Roth IRA. And retires after 50 years. Okay. In 50 years, leaving the investment in the same account. The money untouched. in the same account. Giving 12% interest. Compounded monthly. How much? Tax-free money. Does he have? When he retires. Okay, so let's see. So it's $100 per month. So 12. So I guess the Mr. Goodfather invests $24,000 total. And so what is this $24,000 in total that he's just done $100 per month? So it's not that much money he's putting into the account. What does that come out to equal? Okay, so he's putting it into an annuity. And so for the first, so let's see, for first 20 years. Let's figure out what happens. Okay. So the amount is equal to P 1 plus R to the N minus 1 over R. And that's the formula we have here for a simple annuity. So every month he puts in, what was it, $100? The interest rate is 12% per year, compounded monthly, so every period is just 1% interest. And he does that for 20 years. Well, there are 12 periods per year for 20 years. That's 240 periods. Okay. And so multiply by 100, so that's 10,000 times 1.01 to the 240 minus 1. So that's the amount of money that you have after 20 years. Next, for retirement, let's figure out how much money he has. Well, remember the formula is the amount is P 1 plus R to the N. That's if you do it for N periods. I guess the other one I just wrote it for one period. But of course, obviously, per period, and if it was N periods, it'd be to the N. And so let's do that. So the amount that he initially invests is, well, this. And you're going to do it for, interest rate is 0.01, and you're doing it for 50 times 12. So every year, there's 12 of them. You do it for 50 years, so that's 600 of them. So it's 10,000, 1.01 to the 240 minus 1, and times 1.01 to the $600. And so let's see how much money that is. So how much does that $100 come out to equal? Well, so that's the exact amount. Let's find the approximate amount. So if I do that, 1.01 is 1 times 1 to the 600 times is 38737,597.65. It is approximately, so the $100 per month, and this is only done for 20 years. So $100 per month for 20 years. At retirement, you would have $38,737,597.65 tax-free for retirement. Unfortunately, the average person in the United States has actually $0 saved up for retirement by the age of 55. So the average person in the United States actually doesn't have any. They don't actually start saving for retirement until actually over the age of 55 in the United States. Um, and obviously then it's sort of, if you start early, it's easy to have a sufficient amount to retire with. If you start late, then obviously it's going to be much more difficult. um, Here, if you start early, then you have to invest almost nothing. If you wait to the end, then obviously, you're going to have to put in virtually your whole paycheck. If you do it for 10 years, your whole paycheck for 10 years, you won't make it. Actually, you won't make it unless you have unless you have something else besides that that investment. If you have, you need something else. So you could not. I guess the average person in the United States is assuming they have something else rather than uh, what they're going to retire on. Of course, most people don't, and they obviously have problems in retirement. They run out of money. Okay, so let me give you some additional sort of things. So recall what we had from before. The sum k equaling 1 to n of 1 was n. And we also had the sum k equaling 1 to n of k was n plus 1 over 2. And the sum k equaling 1 to n of k squared, I said was n plus 1 to n plus 1 over 6. Let me give you one more. Sum k equals 1 to n of k cubed is equal to n squared, n plus 1 squared over 4. So let me show how to derive. So before I showed you how to show these by mathematical induction, let me show you how to derive this using the following idea. And so, how to derive these formulas. Above. So the idea is as follows. If you know the first n of these formulas, you can find the n plus first by doing the following trick. So let's try to derive the formula for this second one here. So So let's do that. Okay. So I need to know the sum for the one above it, the sum k equaling 1 to n of n of 1, but we know that, so um, we will always use the following idea. I will look at k squared minus k minus 1 squared. So this is to the first power. To find the formula for first power, you do the squares. For find the formula for second power, you do the cubes. For the cubes, you'd use the fourth power. So you always do one higher power. Okay, well, this is equal to, first off, let me just write out each of these terms. So this is just equal to, plug in k equal 1. So 1 squared minus 0 squared. Let's do the next term. So let's plug in for k 2. So it's going to be 2 squared minus 1 squared. Plus, plug in 3. 3 squared minus 2 squared. Keep going. Let's do the k minus 1 term. So it'd be k minus 1 squared minus k minus 2 squared. Let's do the last term, kth term. The nth term, I'm sorry. Let's do this is the n minus 1. Let's do the nth term, so it'd be n squared minus n minus 1 squared. So notice that the 1 squares cancel, 2 squares cancel, the 3 squares are going to cancel with something over here. The n minus 1 squares cancel. The n minus 2 squares cancel with something before it. So the only things that are left are n squared, are the first term and the last term. This is called the telescoping series. If you've ever looked at some of those old spy glasses where when you look out at it, they sort of expand to a much longer length than what it was originally, or if you've ever been on a camping trip where they have cups that are collapsible and you just expand them to be the length that you want. And so this is called telescoping because old telescopes used to look like this. They used to used to be able to collapse them. So any sort of collapsing type of series is called a telescoping series. Okay, so let me do this. So now that's one way of looking at this. Now let's look at it a different way. And so this says that the sum k equaling 1 to n of k squared minus k minus 1 squared is equal to n squared. Since 0 squared is just 0. Let's look at this another way. So, sum k equaling 1 to n of k squared minus k minus 1 squared. Well, let's use the special product formula. So we know all the special product formulas for adding up, or for taking the powers. And so k is equal to 1 to n of k squared minus. So using the special product formula, I get k squared minus 2k plus 1. So this is equal to sum k equaling 1 to n of k squared minus k squared plus 2k minus 1. The k squares cancel. So you just get the sum k equaling 1 to n of 2k minus 1. We may have done that one, which is equal to, well, 2 times the sum k equaling 1 to n of k minus the sum k equaling 1 to n of 1. Just using the properties of summation that I've given you previously. And so this is equal to, well, the sum k equaling 1 to n of 1 is just n. We knew that. So I have that 2 sum k equaling 1 to n of k minus n is just equal to, well, we said that previously the sum, which is the same sum we just calculated, was equal to n squared. So let's add n to both sides of my equation. So we get 2 sum k equaling 1 to n of k is equal to n squared plus n. Let me factor out an n. And so I get n plus 1. So let's divide both sides of my equation by 2. So I get the sum k equaling 1 to n of k equals n plus 1 over 2, which is the formula that that Gauss got, and the formula that we derived by slightly different methods from just utilizing the fact that we had done it in general for any arithmetic series. So this is yet another way to derive it. I showed it several different ways now. Okay, so suppose you want to determine the amount of money. Well, let's do the following. Problem number 30. Suppose that you win a $37,000, $37,440,000 lottery. And you decide against taking a lump sum payment option of and instead receive $120,000 per month for 26 years. What single deposit should the lottery commission make now to fund your lottery winning? Assume that the commission is able to invest an account that pays, 7.2% interest compounded monthly. How much would you get if you chose the single payment option? The lump sum option. Okay, so let's do that. Well, basically, all I need to do is solve this equation here for P, basically. And so, if I do that, the amount that you must invest is P 1 minus 1 plus R to the negative N over R. Okay, so let's figure this out. So R is equal to, was it 7.27? 7.2% per month. This is per year. So let's divide by 12. And then this will be per month. And so the interest is going to be 0.006 per month. And N is 26 years, which is, well, there are 12 months per year. And so 312 months. Okay. And the amount of money that you would receive every month is $12,000. Okay, so you want to be able to fund this with $12,000, be able to withdraw $12,000 every month from this fund. And so let's see. So A sub 0 is 12,000, 120,000, sorry. It's 120,000 per month. Okay, so $120,000 per month. And the interest rate is 0.006 per month. And we're doing this for 312 months. And we're dividing by 0.006. And so that's the amount that you initially need to invest. And so 120,000 divided by 0.06 is 20 million. 8,000, right? So it'll be 20. Three more zeros. Okay, yeah. 20 million. Then 1 minus 1.006 to negative 312. That's how much must be initially invested, which is approximately one six 906 429.55. And so 906,429.55 is how much they would to initially need to invest. And actually, that's the amount that you would also, that's how they figure out the lump sum. This is both the answer is how much do they need to invest in order for them to be able to take out $120,000 per month for 20 years without running out of money. They need to put in nearly $17 million in order to get at the end this $37 million, $38 million. And so 37, yeah, a little over, so $37,440,000. And so if you chose the lump sum option, they would give you this 17 million instead. Okay, which is basically it's fairly realistic if you look at the lump sums for lotteries or whatever. That's actually a pretty accurate amount. Of course, it changes depending on what they can invest in and all that. But they obviously tell you beforehand what the lump sum is, but that's how they figure it out. So they figure it out is, and similarly, I mean, when you try to lease a car or whatever, they're doing the same thing. They're looking at the depreciation and they put it into basically the same formula. Mortgages, loans. So people were asking for applications of this. Here are the applications. Of course, lottery winnings may not be, you probably don't win too many times, but mortgages and loans, you always do this. So mortgages and loans. Uh, This is the amortization formula for equal payments. You go out to buy a house and you aren't able to pay off all the money to just buy a house outright. So you're going to get some sort of loan. In this course, in this case they call it a mortgage. And so how much do you have to pay per month? Next, maybe you're going out to buy a car and you don't have enough money to just buy the car outright. And so you maybe need a loan. So let's figure out, they then say, well, this is how much money you have to pay every month or whatever. And so things that you have to take out a loan for, this is how they calculate the amount of money you will need to pay so that at the end of a particular period of time, you've paid off all of that loan plus any sort of interest that they may have charged you. And so, if I solve this equation here for P, so just solve it for P, I get the amortization formula. And so P is equal to A0R over 1 minus 1 plus R to the negative n. So that's your formula for mortgages, for loans. So let's do the following example. Suppose you take out a 30-year mortgage of $700,000. So you're trying to buy a house in California, in Los Angeles, and you're able to put down a down payment, maybe of maybe I don't know $150,000, but you still have $700,000 that you're not able to pay off. So you get a loan. You take out a 30-year mortgage for your new home. And this will be at 4.8% annual interest. Compounded monthly. Determine your monthly payments on this mortgage. Okay, so let's do that. And so you're going to take out this rather large loan, and it'd be nice to know that they're actually charging you the correct amount per month, rather than just taking it sort of on faith that they aren't giving you an incorrect amount. And so, because it's a lot of money. I mean, a mortgage obviously is going to be a lot. So let's figure out how much they should be charging you with all of this data that I've given you. Okay, so let's use the amortization formula. Oops. Oh, let me just check something. Let's just check that everyone's okay. Oh, here it is. Okay. $65 grams. Okay. Okay, so let's do this. Hmm. Okay, good. Sorry. So I have P equals A0R over 1 minus 1 plus R to the negative N. And so here, A sub 0 is 700,000. Your interest rate is 4.8% per year, which is 0.48 divided by 12, and this will be then per month. And so the interest rate is 0.004 per month. And N equals 30 years. And so this is 30 times 12 months, which is 360 months. Okay. And so P is equal to 700,000 times 0.004 divided by 1 minus 1 plus 0.004 to the negative 360. Okay, plug that into your calculator. I'll be back in about 1 minute, but nature is calling me and I cannot. And I must answer. So do this calculation on your calculator. I'll be back in about 2 minutes. Bye-bye. Okay, so, sorry about that. So let me put this into my calculator. And so I get that it is approximately oops, 2134.69403.06.475, which is approximately $2,134.69 per month. And so that is approximately what your mortgage is, which is a relatively accurate amount. Yes, occasionally we have to. Okay. Okay. Um, and so, 1 second. Let me. Okay. Okay, so that was your mortgage. I must have clicked on something. Oh, it's way back here. I clicked on that. Aha, so that is your mortgage. So that really finishes off section 15.6. Yeah, the last problems in that section just dealt with mortgages. Okay, let's start section 15.7, which is on Pascal's triangle. Section 15.7, Pascal's triangle.